going to start off today talking about very small clocks. So clocks in the initial little part of the talk that are based on optical fibres, so trapping vapours of either things like iodine, for example, which have really interesting optical spectra, or the alkali metals, such as rubidium or cesium, to build very, very small atomic clocks based on microfabrication technology. So we're going to talk about those sorts of things and then move on to some interesting applications. So as you might have noticed as we're going through, clocks from traditional times, really big things. You can see an elephant with a pyramid as a giant sundial somewhere in Italy. But even the more modern types of clocks you've seen on the optical tables are very complicated and messy sort of things. So our dream was, at some expense in precision, so I'm saying something like 1,000 times inferior to the best laboratory standards, but still serving a very important job in telecommunications and for example, like improving the performance of GPS receivers. We're really interested in building a very, very small clock. And to do this, we're going to exploit this new technology of photonic crystal fibres. So what you can see up here is a cross-section of one of these photonic crystal fibres that we're going to use in the experiments I'm about to tell you about. So you can see that in the middle of the fibre, which looks like the lit up bit, there's actually a hole down the centre of the fibre. It's 35 microns in diameter. So this is a piece of fibre provided to us through a collaboration with the University of Bath, who are capable of making relatively large holes down the centre of the fibre. But because of the interaction of the light with the photonic crystal structure, which is this basket weaving thing, which is called Kagome structure around that central hole, it's still capable of guiding light in a single mode down that hollow core. And if you think about how conventional optical fibre works, where the central core's got a higher refractive index than the cladding around it, this is quite an amazing advance, because normally you would expect that if you've got a lower refractive index in the centre and higher on the outside, then the light, after a few bounces off the surface of that hollow core, would travel off into the glass and will no longer guide down the central core, and certainly it's not going to guide in a single mode when the core is so large like that. So that's the real basis of our exploitation. So the one application I'm going to tell you about is the use of loading up that central core with iodine vapour. And we choose to use iodine, as you'll see, because it's got a fantastic spectrum. It's got absorption lines all the way from 1064 nanometres in the infrared through to 500 and something like low 500s, like 512 or 514 nanometres in the green part, the greeny blue part of the spectrum. So it's got strong absorption lines all over there, and because it's a very large molecule and slow moving, it means that even without undue preparation of laser cooling, we can still get very, very narrow lines, and I'll show you that as we go along. So the typical iodine experiment that's been done for the last probably up to 30 years or so is to essentially get a glass cell that's macroscopic in size and load it up with some iodine vapour, and then basically do a simple spectroscopy experiment like I'm showing in the plot there in the upper right-hand part of the slide. So we basically take a laser, transmit it through the cell, and then detect on a photodiode the absorption lines. If we do that simply, as we'll see in the way I just sort of described, and the problem is that all of the Doppler shifts of the molecules lead to very broad absorption lines. So we do a little trick that I alluded to in the last time I spoke with you, which is essentially to send another beam in the opposite direction through the cell. And that's called a saturation absorption approach. And the idea is that one class of atoms can interact with both the blue pump beam that's going backwards through the cell and the green forward-going probe. That one class of atoms is the class of atoms which is not moving towards the green or the blue, but is stationary in that reference frame. And that zero velocity or zero longitudinal velocity class will contribute to, we'll see both of those signals, and so therefore will behave differently and will be saturated by the fact that it sees twice as much optical power, and so we'll see a little blip from that zero velocity class, which will be much narrower, because it's not broadened by the velocity of the atoms, the thermal velocity of the atoms. So I should also tell you that that's a small cell from our lab that's about 10 centimetres long. But I'll tell you about the performance of some very serious iodine experiments, and they made use of cells that are between 1 metre and up to 3 metres long and something like 20 centimetres in diameter in these laboratory experiments. So that's a really large scale and fragile apparatus that you can't realistically carry around. And I want you to contrast what we're doing with the optical fibre, which still potentially has all the advantages of the big cells, because the fibre can be very, very long, but of course you can wrap it all up and put it in a matchbox, which is super convenient. So the two experiments I was going to tell you, we'll look at the pretty picture, won't we? Can we go back? So you can see, in fact, the green light that's travelling through the iodine cell there, and for those of you with good eyesight, you'll notice that where the beam actually goes through the cell, it doesn't quite look the same colour as the green that's illuminating the rest of the photograph, and that's because the iodine, after being excited by the green, actually goes through sort of a fluorescent decay through a whole bunch of levels, and so the light that you're seeing from the iodine looks a different colour to the input light. Okay, so here are the results of a couple of fantastic experiments. So the red one shows that the Allen variance, the fractional frequency stability of one of these iodine setups that was built at Chiller and Bowler, and also there's another experiment reported there from the National Institute for Metrology in China, which is shown in the green curve, can really be very, very competitive with the best laser-cooled lattice and ion clock standards, the most complicated experiments you can imagine. And all you need is a big, long iodine cell. I think, from memory, I can even read it, the Chiller one was 1.2 metres long, the tube, and the Chinese experiment was a little bit shorter, 50 centimetres long, and then it was very large diameter because they multi-passed the laser beams through the cell 4 times. And so those are really competitive results, but of course on a large scale and fragile apparatus. We want to compete with that, but do it all in a device that can be potentially put in a matchbox and may well serve as a really nice calibration standard for your optical spectrum analyzer or for an optical communications application. Okay. That's all good. So let's give you some sort of characteristic numbers for the comparing a fibre against a glass cell. And in here I'm talking about the glass cell that we're going to use in the laboratory, which was something like 10 centimetres long and with a 500 micron laser beam diameter through there. Well, the fibre is something like 35 micron beam size and is 3 metres long, so we get a very, very strong interaction with the iodine, and potentially we can exploit non-linear phenomena in there as well, because we've got very, very intense light. So we have a much stronger intensity. One of the important things in these iodine experiments is to ensure that the pump and the probe beams are very, very well overlapped, and that their alignment doesn't change with respect to each other, because that induces a whole lot of frequency shifts and is responsible for poor frequency stability in the long term. So the great thing about the fibre is it guarantees that the forward and backward beams are perfectly overlapped in modes because they're guided by the fibre, and also that they can't misalign. So that turns out to be a big advantage in our case. And the other thing we notice is that in our system, the signal is something like 10 times larger, it's 20 times larger than the system in the cell, essentially because we can use a lot more power than you can use in a cell, because we get such an intensification of the light inside the fibre. Let's say the one point that's an issue with the fibre versus the cell is that because the atom's going to keep running into the walls of the cell, or molecules I should say, run into the walls of the cell, we're going to have a limit in the maximum interaction time between the molecules and the light, which corresponds to meaning we can't see lines any narrower than something like 400 kilohertz, which is still pretty narrow by most normal comparisons, and that's essentially because the iodine is so nice and heavy that it's moving relatively slow even at room temperature. Now that seems like a really annoying outcome, but actually turns out not to be a big problem, because collisional shifts that actually dominate the line widths in iodine anyway at the level of a few megahertz, and so this transit time issue doesn't really seem to afflict us so seriously. So the sort of setup we use is we have a laser, and we divide it into a pump and a probe, and then we inject it into vacuum systems that have a vapour of iodine released into them, and the fibres mounted in the other side of the vacuum that actually travels across the room. So this is something in the far future. What we'd hope to do is load the fibre up with iodine, and then detach it from the vacuum system that sealed the fibre, so that we can provide you a piece of fibre that's loaded with iodine, which you can just carry around like a normal piece of telecommunications fibre, but use it as a very narrow frequency resolving cell, which would be very nice. The rest of the things, I don't think we need to go into them. They're just a whole bunch of techniques for eliminating noise, which is essentially doing a pounder in the hall like I locked lasers to cavities previously. So let's travel on. I've got a few photographs here. So the first one is, here's the actual fibre loaded up with iodine, and so you see this beautiful fluorescence from the side of the fibre where the iodine absorbs the green light that's travelling through and re-emits it out the side of the fibre. And a sort of close-up of the actual vacuum system itself. So the probe lights launched through a microscope objective in the foreground of the shot. And then behind this sort of like screw piece here, you can actually see the vacuum system. And what you'll note is, unlike everything else we do in our lab, the vacuum system is actually made of all glass with Teflon valves. The reason we do that is it turns out that iodine is awful stuff that reacts very strongly with almost all metals, but surprisingly including stainless steel as well. And so the problem is that if you build your vacuum system containing metal components, there's a reaction between the iodine that gives rise to other volatile materials that fill the vacuum system and actually mean you can't see the narrow spectral lines that we're really interested in because of collisions between these background unwanted molecular compounds and the actual iodine itself. Okay, so here's a comparison of what you would see typically in a cell, which is shown, so I should show you, start a bit more slowly. So the sort of background wide curve is in fact the Doppler Broadening absorption of one particular line in iodine that the nomenclature is some crazy stuff of molecules that's written up at the top with some line near 532 nanometers that we happen to use. So you can see the Doppler Broaden line is the one that's about 400 megahertz wide that's in the background there. It looks like a broad Gaussian. And then using the technique of saturated absorption, you can get rid of all the Doppler shift and actually just be able to see the underlying Doppler-free lines, which are shown by the two traces shown in the grey and in the blue at the bottom. So the blue at the bottom is from a conventional cell setup, and the grey one in the middle is actually from this fibre material. And I think you can all see that the noise of the fibre system is in fact substantially better. In fact, there's a whole bunch of little resonances that you can see on the right-hand side. Those are real absorptions by the iodine, which you can't even see in the cell. That's one example of how the signal to noise is improved. And that comes about essentially because the fibre is 3 metres long, and we've got this fantastic mode overlap between the two directions, and so we have much less acoustic sensitivity, and we see really nice narrow resonances that are 10 megahertz across. So the idea is that we'll use one of those strong resonances to stabilise our laser by locking it onto one of the taller and narrower peaks in that manifold. And you can also note the power of this Doppler-free technique, which rids us of all of this Doppler broadening that gives rise to the broader line. The reason that there's a multitude of lines is essentially there's a whole bunch of different nuclear spins of the iodine as the interactions of the electrons with the molecule that give rise to something between 15 and 17, depending on which resonance you're actually looking at. Okay. So to give you another example of that, we can zoom in on, for example, here's a little scan over something like 50 gigahertz of the spectrum, and you can see the iodine's got lots and lots of absorption lines, and the... Okay, so here's just another example of one of the other lines, and you can see the very strong hyperfine features in the grey curve, where you can see lots and lots of features which are real ones associated with the molecules, and in the blue, in fact, which comes from the cell, you can't see any of the interesting features. So here's some characteristics of the gas loading up into the fibre. You can see that after we release the iodine, it takes something like 80 minutes to fill the optical fibre, and that's essentially just because it's 35 microns in diameter and 3 metres long, and so it takes quite a long time, of the order of an hour, for the iodine to make its way down the full fibre. If we look at it over a much longer period of time, so this is time after it's released, what we notice is that there's a decrease in in the Doppler absorption. And this is our biggest challenge at the moment, which is the other side, for example, of the fact that the iodine takes a long time to get in there. However hard you try and clean this fibre out by heating it up and pumping on it for ages, there's always contamination left in the fibre, and that contamination slowly outgasses from the hollow wall, and there seems to be an interaction between the iodine and whatever was left on the wall of the fibre, which is causing this decrease in absorption after some time. And unfortunately for us, this has another effect, because as this contamination is released into that system, we also see that the lines slowly broaden with time. So once again, this is over periods of the order of an hour, and we're seeing, or a couple of hours, and we're seeing that the width of those hyperfine lines slowly broaden, which indicate there's some collisional effect of this background gas. So it's a real challenge. We need to figure out how to make the fibre much, much cleaner than we currently do. And we've got a few ideas about passing hot and ultra-pure helium gas, for example, as a carrier to try and drag all of that dirt out of the fibre. So if we can overcome that problem and make sure the fibre is very, very clean to start with, then we suspect that some of these problems will go away. And in fact, if you go into a background calculation, or a back-of-the-envelope calculation, and essentially look up the amount of outgassing you typically get from a piece of Pyrex, which you can find on various websites, then you can calculate that, in fact, we've got something like 70 pascals per hour increase in pressure inside that fibre. And that comes about not only, I suppose, because we haven't really made it clean, but also the fibre geometry really exacerbates that. But by being so small, the ratio of volume to surface area is really not in your favour. So you've effectively got a lot of surface area to volume ratio, which means that the rate of the pressure increase is very, very fast unless you make it clean. So we really need to figure that out. The other issue we see is that the frequency of those hyperfine lines can move around if we change the power that's incident on the fibre, and that's exactly what you'd expect from something called the Stark shift, which is essentially the same effect we were using to trap atoms in the lattice yesterday when we were talking about that. So we need to either control the power into the fibre, or much better, take the iodine system off the vacuum, take the fibre off the vacuum system, and then just basically do the experiment as an all-fibre system, which will minimise the power fluctuations, which we have at the moment because we're trying to make a free space to fibre. Yeah. Okay, so I'll jump over all of that, which is some notes about how we actually lock the laser to the iodine. We've sort of talked about that numerous times, and it's always essentially the same technique. So if we look at the fluctuations in the free-running laser, they're plotted up here on the spectral density of the frequency fluctuation. So it's got a typical laser sort of curve that we've seen many times before, that there are lots and lots of big fluctuations of the order of 10 megahertz or so over hundreds of seconds, and it decreases down. And then what we can do in here is look what our ability to lock and suppress that fluctuations in the lasers are. And that's shown for two curves here. The first is for doing it with the cell, which is shown in the grey curve, and the other way around. The cell, the glass cell, is shown in the blue curve, and the fibre is shown in the grey cell. Now, I've been telling you a story that we should actually be able to do substantially better in our fibre, and we do indeed believe this is true. What you see here is, in fact, that the fibre is more noisy than the cell, and the reason why that was is this was our first go at trying to lock the laser to the cell, which only happened about 3 weeks ago, and we loaded way too much iodine into the fibre, so there was too much absorption, and signals were very, very weak. So this needs a bit of further work, a bit of temperature control on the fibre to prevent us from loading too much iodine in. That was the spectral density. We could also present the same sort of data on an Allen variance curve, and so you can see that over various timescales, I plotted up here the fractional frequency fluctuations, and once again there's a consistency between the spectral density and the time behaviour as you'd expect. And so we're seeing that basically we can suppress the fluctuations of the laser down to parts in 10 to the 10 or parts in 10 to the 11, and we really think you could probably do an order of magnitude better than that, which makes it comparable to to certainly, well, better than any commercial optical frequency standard you can buy at the moment, and yet all of this is potentially compactable into something like the size of a matchbox, which I think is sort of quite interesting and useful. Probably many tasks where people want like a frequency stable laser for some metrology application. So as I said here, the plan is that we really would like to temperature control the system whilst we're loading, in order that we put a controllable amount of iodine into the system, and we need to make a much cleaner fibre, and the plan will be so that we actually pull the fibre off the vacuum system and just be able to present it to you as a ready-to-go cell that's perfectly stable. Alright, so that's our first little chat about one type of microclock. I also wanted to tell you about this other one, which is work that's gone on at NIST by the group of John Kitching. So this is his little microfabricated silica-based device, and the idea is that he's really looking for applications in mobile phone and GPS receivers, which can allow the mobile phone system to work more effectively, prevent drop calls, but also for GPS-based systems, if they lose sight of all of their satellites, it can take several hours to reacquire people's location. And in certain critical applications, you can't afford that. And the idea is that if you can carry a little atomic clock on board, then you can much more quickly reacquire your position once the satellites come back into view, and you can keep the time going even if you can't see the satellites. And so the idea is to make a very compact atomic clock. So instead of the big complicated things we're talking about before, we can do the whole thing on the scale of a grain of rice, which is the size of this device just here. This little square box here is where the vapour of either rubidium or cesium is contained. There's a little photodiode sitting on the top here, and underneath this system is a laser diode that is modulated and injecting its light through the cube, and one sees an absorption feature inside the gas. So I was going to tell you a little bit about how that works. So how does it work? Well, it turns out this works on a completely different scheme from the optical spectroscopy we've been talking about before, but it makes use of something called coherent population trapping, or sometimes it's called electromagnetically induced transparency as well. How does that work? Well, essentially we start with some sort of alkali metal, such as cesium or rubidium, and cesium and rubidium both contain this sort of atomic structure where we have two ground state levels which are separated by some microwave frequency, somewhere in the domain of 3 gigahertz up to 9 gigahertz. And both of these states are perfectly stable. They're really arising from the interaction of the nucleus and the electron spin. And as I said, split by some microwave level. And then we'll have some sort of level up here which is separated from these two ground states by an optical transition. Well, it turns out in that so-called lambda system, 3-level system that we're looking at just here, if one was to excite the system with two lasers, which essentially had a frequency difference that was equal to the ground state energy difference, then we could produce a special state called this coherent population trapping, or electromagnetically induced transparency, such that the light, the atoms stop interacting with the light, or stop their absorption when we reach this condition that the difference frequency between these two is equal to this here. So it's quite complicated to understand in a normal way, but in a hand-waving way, what you might say is that the populations that are in these two levels will evolve such that when driven by the light, the emitted light from this laser interacting with this population is in exactly equal in magnitude to the scattered light from this population being driven by this laser, but in opposite phase. And so those two quantum mechanical amplitudes will actually scatter, and the system will stop scattering light altogether. And that's pretty magic, and it happens under a wide range of conditions. So as long as there's a well-defined phase between this laser and this laser, and as I say, they have a frequency difference which is equal to this ground state, then generally, whether it's amplitude modulation or frequency modulation, which is, well, I should go back, like whatever the means by which you produce these two beams, whatever their phase relationship, you'll still find that the system will evolve into that dark state and exhibit this characteristic. But you might ask, which detunings are important here? Is the detuning from this excited state up here important? And it turns out that that really is not of an awful lot of importance. It just determines the strength of this electromagnetic induced transparency. So you'd like these two things to be relatively close to here. What has been done at NIST is a really smart idea, is that they actually add a bunch of buffer gas to the gaseous material in the little gas cell that they have, in order that all these optical transitions are broadened out, and so this detuning becomes very unimportant. A standard laser diode will be able to be stable enough to stay in resonance with this particular transition. But as I've said, what is extremely important is we have a way of producing two laser beams which have a frequency difference which is equal to this energy difference of these two ground states. How do you go about doing that? Well, it's very easy because we saw it in our first lecture. How do you produce like a carrier and have another laser beam and a well-defined frequency offset? You frequency modulate it or amplitude modulate it, because that will produce a sideband. And so that's exactly what's done. In NIST, they essentially have some laser at this frequency here, and they amplitude modulate it, and it makes a sideband at exactly the right frequency offset. It also makes another sideband at the other side. That doesn't interact with the atoms, so we forget about that one. Okay, what does it look like? Well, here's a plot of how much absorption occurs, how much of the laser light emitted by this modulated diode is absorbed in passing through the cell as a function of the modulation frequency itself, so essentially the separation between these two laser frequencies. And you can see that when the difference between the modulation frequency and that ground state splitting becomes zero, so it's exactly tuned to the two frequency to jump up and then jump immediately down to the other ground state, and you'll see that there's a reduction in absorption. You've got a nice narrow feature. And this feature can be down to like 50 hertz wide, although you should always remember that this is in the microwave frequency, in the modulation frequency, so it's not a 50 hertz wide optical resonance, but effectively a 50 hertz wide microwave resonance. So we can build a microwave clock based on that if we detect that modulation frequency. Except what's really important perhaps, and what allows us to be very, very compact, is that we're not actually exciting the atoms with a microwave signal as in a traditional microwave clock, but we're exciting them with two optical signals which have a frequency difference equal to the microwave system. And the big advantage of that is that pushing microwave signals around requires large structures on the scale of the microwave wavelength, whereas if we do it with optical signals which have frequency differences equal to the microwave signal, then we can do it all using compact photonic techniques. So that's very nice. How well does it work if you're locked to that central narrow feature? So here's the Allen variance, once again for some of these different devices that John Kitching's built. So we have a cesium and a rubidium example here, so there's something on the scale of parts in 10 to the 11, which makes them only about a factor of 10 worse than the large rubidium clocks that were traditionally built, yet all of this happens on a very small circuit board. This more recent work, which was in 2005, they've started modifying the chemistry of the surface of that cell, because it turns out that the interaction between the gas and the surface of the cell is very, very important for the long-term stability. So you see again, one of the challenges of this microscopic devices is that we end up with having a lot of sensitivity to the interaction between the vapor and the surfaces, which is something that was absent in the larger cells before. So just as with the fibres, we see something similar that needs to be resolved there. And to put that just into context with all of these amazing standards that I showed you yesterday, so here's these super stable devices that are at the leading edge. Well, John Kitching's microfabricated clocks just really come onto the very edge, as do our iodine systems on fibres at the moment. So they're really sitting up on the top of this plot, which, if you're a physicist and dream of setting records, makes you a bit sad, but this actually satisfies many technological requirements, and so it still serves a very useful purpose in more industrial applications. So there's another nice thing that one can do with these little microfabricated clocks on really any of those systems, is one can exploit the fact that atoms and molecules generally have a whole bunch of degenerate levels, a bunch of degenerate Zeeman levels, and that if there is an external magnetic field, then you'll find that these various Zeeman levels will no longer be degenerate, will split up. And you can imagine that now in our system where we're driving from one ground state level to the other with our two laser fields, we'll start to see more than one resonance if we split those apart. And of course, when you're building an atomic clock, it's a big job to ensure that you've shielded yourself from these external magnetic fields, because otherwise it's going to cause you frequency shifts. But you can choose to utilise that effect if you don't put the shields in. And so here's an example, once again, with these microfabricated clocks, where there's an external field applied, perhaps some field that one is interested in measuring for geophysical exploration or for medical applications. And we see that as we detune this difference frequency between the two lasers, instead of seeing a single resonance, we actually see a couple of resonances. If we were to measure the spacing between here, we can determine the magnitude of the magnetic field. And in fact, if you choose the right sort of level and you measure all of the spacings of the different microwave transitions between the different Zeeman substates, you can determine some information about the direction of the magnetic field as well, which is potentially very, very useful. So the last example I want to tell you of utilising frequency-style measurements is something that perhaps is not so obvious at all. So how would you go about measuring temperature, for example, with one of these frequency-based systems? And our motivation to do this is that, as you'll see on the last slide that I'm going to give you, is that currently the SI system, which defines all of the units for all of science and for technology, is based on a bunch of ugly standards, like, for example, the kilogram is based on a lump of metal that's held in Paris, and that kilogram is actually known to change in value with time, so that since it was manufactured in the late 1800s, it's actually changed by a part 10 to the 8, which is readily measurable. So the definition of the kilogram itself has changed by a part 10 to the 8, which is, it's almost a stupid thing to say that the definition's changed by a part 10 to the 8, because that's meant to be the defining standard. So maybe it's better to say everything else has changed its mass by a part 10 to the 8 on the globe. And so people want to get away from that. People would like to base their standards on fundamental constants, which certainly we have no real strong evidence that they're changing with time at the moment, so there'd be a much more secure basis on which to build our unit system. So one of the terrible things, in my opinion, in the SI system at the moment is that temperature is based on a particular state of water. It's defined as a certain fraction, the triple point of water when gas, water and steam can coexist. And it's some particular fraction of that defines the Kelvin, and the Boltzmann constant comes from that as well. But you have to get the right type of water, which is called something like Vienna mean sea level water, which has a certain isotopic composition, which sounds like chemistry and not physics. So I want to get away from these standards based on some particular sample of water that's held in some particular location. But we want a standard that anybody can produce at any arbitrary place on the Earth, and which is also very, very stable. So our approach is to suggest a new way to measure temperature, or alternatively you can say that if we bring this sample where we can measure temperature in a different way, to measure absolute temperature in a different way, that we can redefine the Boltzmann constant and then use this as a standard from then on to measure temperature. So how do we go about doing that? What's the basis of the technique? Well, it's a very simple laser spectroscopy technique. So we essentially have a cell of some material, which could indeed be iodine or rubidium or cesium. And instead of using all of our precision techniques we've done before to eliminate the Doppler effect due to all the motion of the atoms, which cause this sort of broad resonances, what we do is actually measure the width of this broad resonance. So for example, here's our sample. We just have a simple scanned laser. We measure the incident light intensity and the transmitted light intensity and divide the two of them. And we'll see some line. which has an intrinsic width due to the fact that all the atoms are actually bouncing around inside that cell in different random directions. But we can relate very simply the observed Doppler width to the distribution of velocities that are in there. And of course, the distribution of velocities relates exactly to temperature, because that's a measure of the microscopic energy of the particles. So if we do this, we have direct access to the average microscopic energy of the particles, which to me is a much more secure foundation on which to define temperature, rather than some sample of water and specifying some fraction of that. So if you do the maths, then you can work out that this frequency width of this line here is basically related to the mass of the particles, which one can know to very high order to the speed of light, which is defined constant in the SI system, so there's no inaccuracy associated with that, and to this product of the Boltzmann constant and the temperature, which is essentially the thermal energy of those particles. And of course, if we were to perform the spectroscopy, we could basically extract this product of the Boltzmann constant and temperature, and we're in a nice position. If we put the cell at the triple point of water, that's the definition of essentially 0 degrees Celsius, 273.14 or something Kelvin, and so what we're measuring corresponds exactly to 273.14 Kelvin. So we can say, we can use that to exactly define the Boltzmann constant. Or alternatively, if we assume that the present value of the Boltzmann constant is correct, then we can use this as a temperature measuring system. Okay, so it's not only us that think this is a good idea. There are two other groups, one in France and one in Italy, who are making use of molecular spectroscopy to do this. And as of a couple of years ago, basically people were operating at the level of 2 parts or so in 10 to the minus 4 of accuracy, which is about an order of magnitude inferior to the other ways that one can try and go about defining the Boltzmann constant or measuring temperature. But just recently, this year, in fact, the French group has pushed the limit down to parts in 10 to just under a part in 10 to the 5, which means that really we're at a level where we're comparable to any other technique. And certainly we think with the alkali metal system, one can push well beyond that. It's really possible to push down to the parts in 10 to the 7 level, where nobody else can measure temperature, primary temperature, with that sort of level of accuracy as it stands by any other technique. So that seems pretty interesting. Essentially, there's a whole bunch of pros to using an elemental system, which is essentially that the strong absorption means that you can use nice small cells which give you great temperature uniformity. The real challenge with using a strong absorber is that there are strong optical pumping effects, and one needs to understand that deeply if you want to make corrections to the spectral line you measure, because you're actually pushing atoms around in the different levels by making the measurement itself. You've got to make sure that the perturbation you're making is sufficiently small. And so you need a good theoretical understanding, whereas with the molecular systems, it's a different problem. You don't have to worry about optical pumping because the interaction between light and molecules is very, very weak. But what you do need to worry about is the fact that there's lots of pressure shifts, molecules bouncing into each other in order to get good signal to noise. And that may well be a complete showstopper in using molecules, because those collisional effects are much more difficult to model than optical pumping effects. Okay, so we take our laser, we inject it through the cell, we measure the incident intensity and the transmitted intensity to measure the spectral line well. The problem is that when you scan and tune your laser, typically the intensity changes, so we in addition build the ability to keep the intensity exactly stable. Furthermore, the next problem we get is that lasers don't give exactly pure monochromatic emission. They generally, especially in the tunable systems, have light at other frequencies, and so in addition to that, we pass our laser through a cavity, which ensures that we only let through a single transverse mode and a single frequency in order to probe the atom so that it's very, very pure. And finally, we need a way to figure out what frequency we're at. And so what we do is we get another one of these same lasers and we stabilise that to a very narrow transition, so we know that we're in a very well-defined place, and we mix the output of this laser with this laser and count some sort of frequency difference over here, so we know exactly where we are on the frequency axis. Okay, what does the picture look like? You know, if we go and measure one of these spectrums, we can measure really nice looking data that looks like something like this, and then it just basically becomes a big fitting problem to determine exactly what those widths are, taking into account the fact that there are other broadening mechanisms, like, for example, the underlying natural line width of these transitions, and so you need to take all that into account, and then you can extract some numbers. And so our results are not so different to the results of the Italian and French group as of 2 years ago. The French group's obviously roaring along and has improved it by about a factor of 10, so we need to play some catch-up now. And essentially, we can estimate, for example, the Boltzmann constant from the width of those measurements, because we held the cell at the triple point of water, so we can generate something like 4 parts of 10 to the minus 4 accuracy in the Boltzmann constant. I wanted to show you that one thing that we do note is these optical pumping effects, so that if we measure, for example, the absorbance of some laser beam travelling through the cell, one would expect from naive theory that involves saturation phenomena that's going to go on in the system to mean that you should follow this blue curve. But in fact, when you go and make the measurements, you see that the system saturates much more quickly than that. And that really comes about because you're starting to perturb the atomic levels and drive things in places where you don't want the level to be. And we've developed recently a very sophisticated theory that allows us to model that in depth. Okay, so right now we're basically moving to new techniques which we think will give us at least a factor of 20 on those last results, and so make it a very competitive technology. Well, the final slide I wanted to finish on was to read this quote from this fellow Christian Bourdais, who said that basically over the last 40 years there's been these discoveries in quantum physics which allow us to think about redefining all of the units in the SI system, of which they're listed down here, based on the principles of quantum physics and relying on the fundamental constants to be constant. And that seems to me to be a much stronger way forward to ensure that the unit systems stay stable, basically. And so this has already started to happen. You know, the time has been, the second was basically based on this hyperfine splitting in cesium, and the meter is defined in terms of that second, the time that the distance light travels in a certain amount of time, which relies on the time definition, assuming that the speed of light is absolutely constant and they fixed it to have a particular value. Recent work is based on quantum standards to define current and voltage, so they're going to be based on well-defined grounds as well, instead of the current definition involving force. And so the real problems are to get rid of these last couple of horrible standards, that is the Kelvin and the Boltzmann constant, which rely on this particular sample of water we don't like. We think this Doppler thermometry should be able to put this on solid ground. And the final one, which I didn't have time to tell you about, was work that's going on in Paris to use atom interferometry to effectively measure the kilogram using photonic principles as well. So the point I'd really like to finish on is that photonics combined with metrology gives you this real power to make stable and accurate measurements. And this is shown in the fact that the SI system, in most cases, is going to be redefined using those photonic metrology techniques. So thank you very much.
Any questions down here? Go ahead.
So you're talking about being able to take these clocks and the fiber clocks, being able to put them inside of something the size of a matchbox.
Yeah.
Can you really wrap the fibers up that tightly?
Yeah, I do.
Oh, okay.
I mean, they don't break, yeah.
And you don't have to worry about bending clocks?
I mean, in fact, they'll bend a lot more than that, and the present problem is just the plastic on the outside that essentially causes you to break the fibre. So perhaps it's not really our forte. We don't manufacture the fibre, so we'd ask the bending loss does not become serious in those, because that photonic crystal really keeps the light going much more. It's much more constraining than just a refractive index contrast So the bending loss can intrinsically be small. I mean, if I actually try to do it with the current fibres we've got on there, I'm sure we'll break them. But that's just because of the big, thick acrylic layer on the outside.
Any other questions, go ahead? No.
With the Holy fibre,
Yeah.
the sort of air gaps around the outside in the mesh,
Yeah.
are they connected to the central hole? I mean, when you evacuate it, do they get evacuated or are they still leaking slowly into the central hole?
Right, so they're completely separated from the central hole in the glass, so in the cross-section, if you like, of the glass. The issue is that all of that comes into our vacuum system, so we do evacuate those holes and load them at the same time. We're loading various elements and molecules in there. In the iodine case, it seems like it doesn't shift the characteristics of the fibre at all to have a bit of iodine in those holes. But we did find that in rubidium, for example, the fibre actually stops gliding if we load those holes up with metal. So what we do is we actually collapse. So basically we collapse the holes first. So the advantage is you heat the end of the fibre, and because those structures are smaller, they collapse first before the central hole, and then we mount it in the vacuum system. We can load just the central core, and then you can cut that end off if you're going to join it to another piece of fibre after you take it off the vacuum system. So it sounds like chemistry, but it seems doable. It's solving the problem.
Go ahead.
You said for the temperature measurement, that optical pumping might be a showstopper, meaning like heating or bouncing or moving the atoms, making the pressure. Have you predicted a fundamental limit due to that, or?
So there is this issue to do with actually doing like pushing on the atoms, which is so there's that sense of optical pumping. We haven't calculated the limits associated with that. So the one that we're calculating is to do with the fact that we move them around the levels. And so that actually makes a distortion in the Gaussian that we expect. So we actually see the shape of the absorption curve change slightly, which is due to the fact that we're actually just pushing the electrons around to different levels as we're scanning the laser. So that causes a modification to the shape. And so one needs to be sure that you're not perturbing that at the level of half a million. So I think that's all good actually. In using rubidium and cesium, we've got plenty of signal to noise. So our calculations suggest that this half a million level where everybody's interested to get to, that's not a big problem. But the molecule people have a real big problem at that level, at the few parts per million level, because of collisions that are very, very hard to model. So they've got a much bigger problem, I think.
All right. If there are no more questions, let's thank you again.